We're going to talk now about index manipulation. So I'm going to try to tell you the basic things you need to know to work with indices. And the idea of indices is that they are labels for objects, and they're particularly useful if you have a collection of objects that you need to label. So our indices are labels for objects, and the labels are going to be called I, J, K, letters of the alphabet, L sometimes, M, P, these letters, and they are labels, and they take therefore values, and the values that they take values are either 1, 2, and 3, and that's because we work in a space with 3 spatial dimensions, and therefore we'll have 3 values, and that's pretty useful. So first example is, for example, if you have a vector A, you would have 3 components, A1, A2, and A3. Now, if we want to talk about the components, we have labels. The labels are 1, 2, and 3. So we'll represent this as the objects AI with I equals 1, 2, or 3. And these are the 3 values, A1, A2, and A3, because I runs over those things. So AI represents an object. If you have a vector B, B1, B2, and B3 are its components, then BI with I equals 1, 2, and 3 again are these objects. Now, things can be a little more general. So, for example, the objects here were vectors and their components. So another possibility is what we sometimes call the vector Pauli matrices, which really means sigma 1, sigma 2, and sigma 3. Now, each one of these is a 2 by 2 matrix, but still it has 3 labels. There's 1, 2, and 3 2 by 2 matrices. So these are the Pauli matrices sigma I, matrices, and they're 2 by 2 matrices. That never shows up here. It's just the fact that there are 3 of them, and we label them again with an index I that can run from 1, 2, and 3. There are more complicated objects that we can label. For example, you can consider a 3 by 3 matrix, M, that has components M11, M12, M13. Well, you could fill all of them, M31 up to M33. So how many things are there to label here? Well, there are 9 objects. It's a 3 by 3 matrix. So 9 objects to label, and we label them as Mij, with I taking 3 values and J taking 3 values. It's a total of 9 objects, and they're the entries of this matrix. So by using indices, we can talk generally about a particular component and just manipulate it in a more easy way. So let me begin by talking about a simple operation which we use indices, is the dot product. So what is the dot product? The dot product of 2 vectors A and B is by definition A1 B1 plus A2 B2 plus A3 B3. Now, you can see that the indices allow you to write this even more quickly as the sum over I equal 1 to 3 of AI BI. And here comes a thing that everybody does, which is a summation convention. Each time you have an index that is repeated, we usually mean that they're supposed to be summed, as here. So we actually don't write the sum. We just write AI, BI, And by this, because there's a repeated index, we say that they are supposed to be summed. That's a convention for working that was apparently suggested by Einstein. So it's repeated indices. Repeated indices are summed over the three values that you can have. Now, there is another object, another kind of matrix that is useful here. We represent the identity matrix by what is called the delta tensor, or the Kronecker delta. Delta. So this matrix delta, or the identity, is 1, 1, 1, zeros everywhere else. And you can think of it as delta 1, 1, delta 1, 2, delta 1, 3, delta 2, 1, delta 3, 1. Oh, well, I'm not going to write the 9 of them, but to delta 3, 3. And as you can see here, well, there's zeros everywhere except in the diagonal. So we can put the rule that tells us how to use the delta function. So we'll say that delta ij is equal to 0 if I is different from j, and is equal to 1 if I is equal to j. Now that is a pretty reasonable thing. You can see it here. Delta 1, 1 is supposed to be 1, but delta 1, 2 and delta 1, 3 are supposed to be 0, and they're 0 because the indices are different. So we can ask a couple more questions about delta functions. Let's go like this. Question: what is delta II? Can be confusing here what this is, because this index seems like it's the same, so you might think, oh, it's 1, but you shouldn't say that, because you should remember the index convention. Delta 1, 1, delta II is equal to delta 1, 1 plus delta 2, 2 plus delta 3, 3. Because the index is repeated, it should be summed. So, but this is 1 and 1 and 1, so this is 3. So delta II is equal to 3. Another question. Simplify delta ij times bj, where bj is arbitrary. So here you have one index summed and one free index. That means that this labels a collection of 3 objects, because I, which is the only free index, takes values 1, 2, 3. So there are 3 objects. J is always summed. So you don't get more objects from this. So what is this really? This is delta I times 1 times b1 plus delta I times 2 times b2 plus delta I3 times b3. And you can ask, if I is equal to 1, what do you get? Well, if I is equal to 1, this is 0 and that is 0. But this survives, so you get b1. If I is equal to 2, well, this is 0 and this, you get b2. And if I is equal to 3, you get b3. Therefore, whatever I is, you get that b. So what have we shown? That delta ij bj is equal to bi. This is a very important property, and you will use it endlessly. Let's box it. So the delta, Kronecker delta, when it has a common index into another object, it simply copies the first index and you can forget about the summed index. So it's a very fascinating object. So we had the Kronecker delta. We've introduced the Kronecker delta. It's defined this way. It's a nice object, and we have a property here. So, so far so good. There's another object that is pretty important, which is the epsilon symbol. So that's another very useful object. Let's put it in blue. So what is the epsilon symbol? Well, you have vectors, things with one index, matrices whose components have two indices, and now we're going to introduce an object with three indexes, an hypermatrix, a matrix. You can think an array in 2 dimensions. This you could think an array in 3 dimensions. Epsilon I j k. So the object is an object that has 3 labels. Since each label can take 3 values, 3 times 3 times 3, there are 27 values that you need to specify here in order to figure out what this epsilon is. So that's a lot of values. But actually, the epsilon symbol, that will be pretty useful for us as well, is required to be totally antisymmetric. Antisymmetric. Notice the Kronecker delta was completely symmetric. Delta ij is the same as delta ji. You can see that from the definition. If they're different, the order won't matter. If they're the same, the order won't matter either. But this epsilon is totally antisymmetric. And I want you to realize what that means, actually. This implies that, for example, or means, as a definition, that epsilon ijk is minus epsilon jik, where I flipped the first and second indices. So whatever these indices values, the values they take, if you flip the order, you get minus what you had before. But totally antisymmetric means that you can do that flip with the other indices as well. So for example, epsilon ijk would be minus if you flip now the third and second, kj. So let's use color. Here I flip this 2. Here I'm flipping this 2. And each time I get a minus sign. Actually, what if you flip the first and the third? Actually, you do get a minus sign as well. So let's do that slowly. Epsilon ijk is minus epsilon jik. I'm moving the I towards the right. Now the I and k can also move because the second and third you can move. And you get another sign, so you get epsilon jki. But I wanted to exchange the I and k, so I still have to move the k across the j. So I get a minus epsilon kji, demonstrating again that if I also flip these other 2 indices, k and I also get a minus sign. So totally antisymmetric really means that whatever 2 indices in an object you flip, you get a minus sign. So this is a very nice thing. Now, you can see actually here, it's kind of interesting to notice. Compare this one and this one. If you do a cyclic reordering, you see I, j, k here have a cyclic ordering. If you do jki, so in the same cyclic order, I, j, k, think of them in a circle, I, j, k, I, j, k. So jki is the same as the original epsilon. So cyclic rearrangements don't change the sign on the epsilon symbol. So, all right, so this is what we demand from this epsilon symbol. Now, because of this total antisymmetry and because the indices have only 3 possible values, you actually get into a situation where this is very constrained. So, for example, note that epsilon 1, 1, 2 is 0 because you have 2 indices that are the same. So if you would use this property, it should be equal to minus epsilon 1, 1, 2, and an object that is equal to minus itself is 0. So epsilon 1, 1, 2 is 0. And it's also epsilon 2, 1, 1 is 0, and epsilon 3, 3, 2 is 0, and epsilon 2, 1, 2 is 0. And all of them are 0 unless all 3 indices are different. But you have 3 indices and 3 possible values. So basically, the only thing you can do is to have epsilon, say, 1, 2, 3, or epsilon 2, 1, 3, or epsilon, say, 1, 3, 2. And you always involve 1, 2, and 3. Those are the only ones that you must involve. Because otherwise, if you don't choose them differently, the thing is 0. So these ones are the non-zero. There may be a few more. But then it gets very easy. We declare that this is, by definition, 1. So this is going to be our definition. And with this definition of 1, then this one doesn't have to be defined because it's negative of this, minus 1. 1, 3, 2, well, you flip 3 and 2, so it's negative of this one, and you can calculate all of the others. So at the end of the day, this epsilon symbol is this hyper matrix, cubic matrix, but it has 27 values, but actually telling one value is enough, and it vanishes almost always unless all the indices are different. So what is the use of this epsilon symbol? This epsilon symbol is great for cross products. So this is what we're going to do now. We're going to do cross products. So we're done with this page, and let's move on. You have all your formulas here. Let's do cross products. So how do we do cross products? Let me remind you of how you did those things. So cross products. So you have the cross product of a vector A with a vector B. Some people like to calculate it with determinants. It's kind of not very elegant, but it's okay, it's effective. You do this, put the unit vectors in the first row, the first, second, and third components of the first vector, and then the 3 components of the second vector. And you just calculate the determinant. So you get x hat times a2b3 minus a3b2 plus y hat, well, it should be with a minus, but then I will take care of it by multiplying with the other order, a3b1 minus a1b3. And the third one, let's write it below, z hat, that comes with a plus a1b2 minus a2b1. It's a rather complicated formula, but actually there's nothing too strange about it. You can also remember it by heart because you sort of go cyclically. So the first component, then you go 1, 2, 3. So then you use the 2 and 3, and you go a2, b3 minus the opposite. Then the second, then you go cyclically. 2, 3, 1. So 3, 1 minus 1, 3. And then the third, then you go 3, and cyclically you go 1, 2, minus 2, 1. So you can think of the numbers 1, 2, and 3 cyclically ordered, and sort of you run it this way, and the formulas go: the first component, you go 2, 3, minus 3, 2. The second component, you go 3, 1, minus 1, 3. The third component, you go 1, 2, minus 2, 1. Anyway, we can write it that way. So A cross B, the first component, I'll put a 1 here, is A2B3 minus A3B2. The second component, A cross B2, the y component, is A3B1 minus A1B3. And the third component, A cross B3, I should draw the vectors everywhere. A cross B, the third component, is A1B2 minus A2B1. Now, okay, so what the epsilon symbol does is allows you to write this more compactly and then manipulate it. So here is the property that, in fact, relates the cross product to the epsilon symbol. So A cross B, the ith component, is actually epsilon ijk AJBK. And it's a very important formula, so I'm going to box it. Now, if somebody gives you a formula like that, you must test it. So let's test it. So a test, let's go. A cross B 1 should be equal to epsilon, well, the I is copied 1, JK, AJBK. Now, it seems like we have to do a lot of work. I have to sum over 3 values of J and sum over 3 values of K. You see, 2 repeated indices mean 2 repeated sums. But that's not too difficult, because remember, the epsilon symbol here has a 1. So the other 2 things, if they're to contribute, must be 2 or 3. So actually, there's only 2 possibilities. They have epsilon 1, 2, 3 times A2B3, because J equal 2 and K equal 3, or 3, 2. So plus epsilon 1, 3, 2, A3B2. But this is 1. Epsilon 1, 2, 3 we define to be 1, so it's A2B3. And epsilon 1, 3, 2 is minus 1. You can reorder this by exchanging the 3 and 2, so minus A3B2. And this is exactly what we had here. So this formula did work doing the sums, and it produced for you the formula that you wanted. So this is excellent. We can trust this. Well, you should do the other 2. It's a good practice, and will help you make sure that you know what you're doing. So we have the cross product, therefore, has been defined. And with the cross products, now we have an ability to do more interesting things. Now, one thing that we usually use a lot is a very curious identity. It involves the product of 2 epsilon symbols, I, J, K, and another epsilon symbol that shares with this one index. One index is the same, so one index is copied, and it's summed over, but the other 2 are different, P, Q. So whenever you have this situation in which you have 2 epsilon symbols that share one index, there is a great possible simplification. And this is equal to delta J, first non-repeated index here with the first non-repeated here, P, times delta KQ, the third with the third, second with second, third with third, minus the Kronecker delta of second with third, delta Kronecker delta of K, which is third, with second, P. So this is a very, very useful formula. You could say, how do you prove this formula? Probably the simplest way would be just to check it. It's not too much work to check it. And you can do some tests of consistency. For example, if you look at this formula, you should say, well, this is antisymmetric in J and K. Is this antisymmetric in J and K? So it should change sign when you change J and K. Well, if you change J and K, this would become delta KP, which is here, and there's delta JQ, which is there, and it appears with a minus sign. So this is properly antisymmetric in these two indices. This is also properly antisymmetric in those two indices, so you don't have to check many cases. And the result is this. There is, in fact, the formula for the product of two epsilons that share no indices whatsoever, and it's given by 6 terms with 3 delta Kronecker deltas each. But we will have really no use for that formula, so let's leave it like that. So this is a curious identity. You will use it a lot this semester, so you should remember that there is an identity, and you need not remember it by heart, although it's very simple, because when you have an index which is the same, then you just put products of Kronecker deltas in the right position. So there's a simple corollary of this equation that follows when you take 2 indices to be the same. So there could be 3 indices that are totally different. It's a formula that I didn't write. 1 index is common, 2 indices common. For that, you simply take P equal to J, and then you will have epsilon ijk epsilon ijk. So what is that equal? Well, I must just put P equals to J. So I have delta JJ delta KQ minus P equals to J, so I'll leave it like that, JQ delta KJ. What is this? Delta JJ, you may remember, that was 3, so you get 3 delta KQ minus. Remember the copying property of a delta function. If you have a delta, a Kronecker delta is not a delta function. You have a Kronecker delta here and a common index, it copies the other one. So the J disappears and the Q is copied into this here. So you have a minus delta K, and instead of the J, you copy the Q. So 3 delta KQ minus a delta KQ is a 2 delta KQ. So it's a nice formula, so let's write it again and box it. Let's write it here. So what do we have? Epsilon ijk epsilon ijk is equal to 2 delta KQ. And it's used a little less often, but it's kind of nice to see that you can do that. Then if the 3 indices are the same, if you now say K equal to Q, then you have epsilon ijk epsilon ijk, and K equals to Q would set this equal to 3, so you get 6. And that makes sense. There's 6 possible ways of constructing an epsilon with a 1, 2, 3. 3 ways to choose the first position, 2 ways to choose the second, and 1 way to choose the last. And then there are 3 terms. They're all squared because products of this epsilon appears twice, and therefore it's a 1 or a minus 1 square added 6 times, which gives you 6. So that's that. So we have this identity, and you might say, well, when do I use it? Well, you use it plenty, but I will do a famous application. Calculate or simplify the triple product A cross B cross C. So you want to know what is A cross B cross C, if you can simplify. Now the cross product of a vector is a vector, and another cross product is still a vector. So this is supposed to be a vector, and you want to know if there's a simpler way to write it. So let's calculate it. So how do we do it? A cross B cross C. You decide that you're going to calculate the ith component of this, because the only thing you know is a formula for the ith component of a cross product. So this would be, by the formula, epsilon I j k, the first vector with the second index, and the second vector with the third index. So the second vector is still B cross C. K. So I should put arrows here, make it look nicer. So we're not done, because there's still another cross product here, and we can use a formula again and get another epsilon, and then you can imagine that we're going to require this formula for the product of epsilons indeed. So here what do we have? Epsilon I j k, a j, and an epsilon k p q. Don't make the error of putting an I or a j, in particular an I, because the I is a free index, it shouldn't be used. A j is already been used, so you should put two new indices, pq, and you have bp cq. Now I have the product of two epsilons, but not quite the way they look up there. Let me write them here. In here, the common index was the first. Here, the common index is last here and first here, so it doesn't quite look the same. And then the other two indices are different. But this is not a big problem, because certainly we can move the k. One flip with a j gives us a sign. Another flip gives us no sign. It's the fact that the cyclic order doesn't change. So this is really epsilon k j, k I j, epsilon k p q, a j b p c q. And now we are in this formulas territory. We have the same index. The same index is the one in the first position, and therefore we can use the identity. So what do we have? Let's write the Kronecker deltas. Delta IP, delta JQ. Second with second, third with third. Minus the alternate. Delta IQ, delta JP. Times AJBPCQ. Now we have to do distributive law. That should not be a problem. Let's do the first. Delta IP would copy an I into this term, so you would get a BI, and the delta JQ would set J and Q the same here, so you would have AJCJ. This is the first term. The I was copied into the P, the JQ was copied into the C. Minus a delta IQ, so the I must be copied into the C, CI, and delta JP, so AJ, and we can copy it into the B, BJ. Then you recognize that this is BI times the dot product of A with C. And this is CI times the dot product of A with B. So this is really it, because we have the ith component of this is the ith component of B times this number minus the C component, the ith component of C times this number. So we can forget about these components and just simply write the identity as A cross B cross C is equal to B times A dot C minus C times A dot B. And that's a famous vector identity that was derived with these methods of index manipulation. So basically, we're getting to the end of what I wanted to tell you about this. This is just a basic introduction to indices. The only way to really learn how to work with indices is to use them and to practice and to do lots of exercises. Now, at this moment, the indices appear like a very neat thing in the sense that allow us to manipulate lots of objects all at once. When you write an equation like this, you're writing 3 equations for I equal 1, 2, and 3, and you're including sums and very complicated things. So you're certainly gaining in manipulation power. But the indices, at the end of the day, have a deeper meaning in that they reflect how objects transform under changes of axis used to measure them. So these objects with indices are called tensors, and tensors transform in nice ways under, say, changes of coordinates, rotations of your coordinates. So there's a nice story to be developed there, and we'll see some of that in this course. But first things first, you really need to be comfortable manipulating indices, and that's what I aim to do here. All right, that's it.